This is a good exercise. So check that for every m, the gap is positive, so that you have that inequality for some time. Okay? So given m, check that the sequence lambda k, written that way, square root of k squared pi squared plus m, fulfills the gap condition in the theorem of gamma of Ingham for some gamma depending on m. Okay? Okay, so we stop here for a short break and we continue in 15 minutes. Okay? So it's now 4. We continue a proof he did. Is very much related to this Shannon business we discussed the other day, in some sense, right? I think it's here, the proof. So he said, okay, I have to deal with general series from minus t to capital T. I can do a change of variables here, right, with a new variable t, say, which is s pi over t, and then I can, without loss of generality, I can reduce to the case where capital T is pi. Okay? This is just a change of variables. And then you name this the new lambdas that you get after multiplying by t over pi by mu's. Okay? This is what you get. Okay, so then the question is whether for t greater than, right, 2 pi, you have this, provided the gap, right, is gamma. Okay, so this is just a normalization. And now you start, and you say, you see, this integral from minus pi to pi of this square is slightly greater than the integral you get when you multiply here by h, where h is this cosine function. So this is really what I was telling you yesterday about the Shannon function. So Ingham realizes that dealing with this integral from minus pi to pi with an it will be harder than considering a function h from minus pi to pi, which is like this, right? And this function is cosine t over 2, right? This function is taking the value here 1 and 0 here, right? And then if you extend this function by 0, right, then you can say that this integral is greater than this. Okay? So you pass from an integral defined on the interval minus pi pi to an integral defined everywhere. Okay? You are losing a little bit, right? Because 1 is better than h. H is vanishing near the boundary, right? 1 is better than h. I'm losing a little bit. But the advantage now is when I expand this, is that what I get here, right, is simply the double sum of the coefficients an times the conjugate, capital K, where capital K is the Fourier transform of a small h at mu n minus mu m. Why? Well, develop that. What is this? This is the modulus of this complex number, right? By the conjugate, right? When I take the conjugate here, I have to take the minus, right? And then I get a double sum of an bar integral of h exponential I mu nt exponential minus I mu nt. And this is what? This is the integral of ht exponential I mu n minus mu nt, right? And then you all agree that this is the definition of the Fourier transform of a small h at the values mu n minus mu m, right? Great. So if I call this capital K, that's it. Now, of course, here I have a double sum. I identify the square terms, where I'm taking simply n equal to m, the diagonal terms, and they are multiplied by k0, and then I have all the off-diagonal terms, right? Okay? Now the question is that I like, out of here, get something that is positive, right? Let me remind you that my goal was to prove that, I was getting an upper bound on the sum of the squares. Of course, the diagonal term is giving me something very nice. But there are all these off-diagonal terms in which there is no sign, and they could completely contaminate, make me lose the quadratic term in here. So to understand this better, I have to look to what is the Fourier transform of this function h. Please do it as an exercise. Check that the Fourier transform of this function h, as defined by Ingham in that way, is precisely this kind of function, which is very close to the Shannon function, right? So yesterday we said that the Shannon function was sinc sinus x divided by x. So here you have a cosine function divided by 1 minus x squared. It's similar. Again, you pay the price of the principle of uncertainty, right? I have decided to take here something of compact support, right? I could have taken the characteristic function, but then the decay will be only 1 over 5. Here I have a faster decay, 1 over 5 squared, right? You see what I mean? So what is the decay as phi goes to infinity there? 1 over 5 squared. I have a quadratic decay. While in the Shannon function I had a 1 over x linear decay. Okay? So here I have a better decay because somehow I have here less steep concentration. The Shannon concentration is the maximal one. Just cut it off, then I get a slower decay. This is in agreement with the principal uncertainty. But definitely, you can choose any other function h with compact support. You can choose the one you like if you are able to improve the proof. I doubt so, right? Many people have tried this, and I think there was no success on improving the original proof of Ingham, right? But in principle, the key is that you are working in a finite interval, that's for sure, because you are coming from a observability property for a wave-like equation. You are working in a finite time interval, so you are making measurements in a finite time interval, and out of this, in order to manipulate that finite integral, you are allowed to introduce a weight, right? But this weight, of course, has to have compact support to be able to relate the integral in the bounded domain with the integral over the whole real line. Okay? Very good. Okay, so now the question is whether with this expression of k, which is this quadratically decaying function, you have enough decay on k in order to, guarantee that this term here can be bounded above by this. You see? Now we continue a little bit. I say, well, what is the value of k0? Well, k0 for phi equals 0 is clearly 4. So this diagonal term gives me 4, right? this off-diagonal term, I can use Cauchy-Schwarz, right? I can write it that way. So yet, what I need to do is to check that for any n, this 4 here is dominating all this sum, right? So what do I get in this sum? I get the difference of k on mu n minus mu m. And this is where I see the role of the gap condition, right? Because what happens in here? So this difference only appears for the off-diagonal terms when m is different from n. So the value in here, in modulus, is at least gamma, right? For m equal n plus 1 is gamma. For m greater is 2 gamma, 3 gamma. So the values here are decaying. And how does this function look like? This function looks like this. So this was h. And this is k. Right? And when does this vanish? When phi is equal to 1/2, right? No?
Yeah.
Is it phi is equal to 1/2, something like this, right?
Yeah. The denominator.
Huh?
Denominator goes to 0.
Yeah. So then
The next one.
okay, so it has this kind of shape, right? You can check details, right? How does k look? And then check is that way. And the decay is quadratic.
I mean the cosinus part is linear in 1/2 to 0, but the part 1 minus 4 psi square is quadratic.
No, this is a standard intuition, but this is not correct because this is linear as well, because this is 1 plus 2 phi times 1 minus 2 phi. They are both linear. Yeah. Okay. Anyhow, the function k starts taking value 1, it goes down, it has a number of zeros, and then it decays polynomially, right? So now what is the game to play? The game to play is that the gap here is enough to make sure that, you know, all these values are bejoined a given threshold so that all these contributions add sufficiently small. And this is actually what happens. So then I use the upper bound on the cosine function, which is given by k, is 4 divided by 4 mu n minus mu m squared minus 1, and I add this series carefully, and I see that indeed, you know, because of the choice that has been done on the gap and on the time, all this adds to a positive constant, right? And actually, you see that in this way, not only you get an estimate, but you can actually quantify in a completely explicit manner the estimate you get. So in particular, you see that in the proof I have done here, in the proof I have done here, the constant here is the same for all sequences with the same gap. So you give me two wave-like models with different spectra, lambda and mu, but both of them have the same gap. Because of that, you can guarantee that both of them are uniformly observable, right? So this is also interesting when you are dealing with, you know, systems depending on parameters, and you have to deal with the robustness of, you know, the observability inequality with respect to, you know, parameter variations. As soon as the spectrum is uniform, the gap of the spectrum is uniform, the observability inequality is uniform as well. Okay? So this is a very nice way of proving observability inequalities based on spectral analysis, Fourier series, non-harmonic Fourier series, and then, using this kind of Shannon-like idea in order to get a good measure of how the gap influences the observability inequality, and that's it. Okay, good. Let's then move to the next topic. This is important as well. Be careful. For the following reason, I said, okay, I need to compute the control for the wave equation. I know this will be possible for t greater than 2. Now, I need to compute the control for the wave equation. I take a v, right? And this v is going to be the normal derivative of the solution of the adjoint wave equation, where this adjoint wave equation is computed by taking the specific initial data that correspond to the minimization of this functional, in which I'm taking the quadratic part, the observability, quadratic form, and here in the linear part, the initial data to be controllable. Okay, but now you say, okay, now you ask me, I have to compute this v. Of course, I cannot do it by hand. Maybe in some very particular cases, I could do it by hand. You take, for instance, exercise, compute the control for t equal 2. For t equal 2, because this pure periodicity, you can write the control by hand. But as soon as there will be some kind of perturbation, as this mass I added, m, that introduces some perturbations in the spectrum, you will not be able to compute it anymore explicitly. You have really to rely on the minimization of this functional. And then to minimize this functional, you need to do two things, basically, right? One is you apply an steepest descent algorithm to minimize capital J, and then in every step of this iterative descent algorithm, you have to solve the wave equation, but you don't know how to solve the wave equation. What you can do in the computer is to solve some finite difference or finite element discretization of the wave equation. Okay? So what the algo says, so the algo is that way. Is v is equal to phi x1t, and the phi is associated to the minimization of j, and to minimize j, what you have to do is what? Out of some initialization of phi 0, then you iterate, right? According to this gradient descent formula, you iterate, right? But then, in every iteration, then this means solving the wave equation. And in fact, in practice, I cannot solve wave equations explicitly. I have to replace this by, say, finite difference, say, version. Right? But I have here all the ingredients to do it. Okay, good. Now let me think on this differently. Sometimes you talk about this with people that are not very fan of mathematics. They will tell you, well, all this is very complicated, because in the end, you see, the criticism will be, here you have to deal with wave equations, energies, Sobolev spaces, observability, velocities of propagation, Ingham inequalities, plenty of analytical tools. And in the end, you are telling me that in the end you have to go down to the finite difference version of the wave equation, which is a finite dimensional system. So why don't we, from the very beginning, say, I don't deal with the wave equation. From the very beginning, I reduce the wave equation to a finite dimensional system, and I apply the Kalman-like understanding we got. Right? This is what people like to do. This is why, in control engineering, there is so much terminology about input and outputs and this and that and black boxes, because people would like to reduce all the needed theory to, a manual in which you say, well, in problem P11, you apply method M13, and then, that's it. Okay? So people are trying to produce black boxes that you can use, like in MATLAB, right? That you go and say, okay, what do you want to do? Feedback stabilization of that. Okay, I use this and then I got it. Okay? I don't need to go into the details. Okay, let's try to do that, which is worth. But it's important to try to do it once to be able to see what are the limitations of each approach. So one of the limitations of this approach is that if you have to do everything, you need plenty of theoretical understanding of a number of things, right? Even Ingham. Okay, now let's do it straight. I say, listen, because in the end I have to plug everything in the computer, and my computer doesn't know about wave equation, but rather about finite difference discretizations of the wave equation, I do it from the very beginning. And I discretize this wave equation into this finite difference discretization in a space of the wave equation. I keep continuous in time just to make it more simple. And this is just a finite difference grid with uniform stress size H. Okay? So what I'm doing is this. I am replacing the flexible chord of the guitar by this semi-rigid string, right? In which, actually this is the way that D'Alembert wrote the wave equation. So now we call it finite differences, but this is the way D'Alembert got the wave equation. He didn't know PDEs, but he knew Newtonian mechanics. And then he said, how is going to be the vibration, the dynamics of n particles interlaced by a string? And he wrote that, the acceleration of each particle is going to be equal, to the balance of forces, and he got this semi-discrete wave equation. Then he said, hand waving, this corresponds to somehow second order variation in space, and then he got this, magic identity, 2 time derivatives equal to 2 space derivatives. So you see that somehow mechanics and numerics merge, right? There was mechanics from finite mechanics to continuum mechanics. There is a limit process there, and then numerics is like coming back. Okay? So definitely, and you see this kind of finite difference modeling is used very much in practice, right? So sometimes, yes, models are continuous, but some other times we just make them discrete, right? So this building, Melia Hotel, you look from outside, how does it look? It looks continuous or discrete? It looks quite discrete, right? It's like a cube, right? It's like a shoe box, right? With some, hyperplane. So maybe there is a lot I could do with discrete modeling about the, the behavior of that building. Maybe I don't need continuous mechanics for everything which is related to, to the nature of this building. Okay. So now I could look to the discrete analog of everything I have done, and well, of course, I will get the natural discrete version of the functional j I was considering before. In particular, I will have that the discrete version of the normal derivative is given by phi n over h, right? Why? Because in this numeration of the nodes, the left extreme is given by the index 0, the right one by the index n plus 1. All the other internal nodes go from 1 to capital N. The gap is given by h. Because of the Dirichlet boundary condition, this one is 0 and this one doesn't move. These two extremes don't move. So phi n plus 1, which is giving me the vertical displacement of this, say, last little point, n plus 1, doesn't move. Phi n plus 1 is equal to 0. So this slope, which is the approximation of the normal derivative phi x at x equal 1, is simply, as written here, phi n plus 1 minus phi n divided by h, which is minus phi n divided by h, because phi n plus 1 is equal to 0. Okay? So this is the kind of functional that corresponds to the problem I am considering. And then I will need to, make sure that the corresponding control, the discrete control, is something like this, right? Okay, good. Fine. So if I am not being very precise, right, I say from the very beginning I replace the wave equation by this discrete wave equation. I take the corresponding functional here. I minimize this functional and I will get a control. Why is that? Because in this case, the observability holds immediately. So my claim is that, let's think a little bit on this. This functional is coercive. The observability for that problem holds immediately. Why is that? Well, this is the notation, so this is the string. This is the node x0, and the displacement here is phi 0 is equal to 0. This is the node xn plus 1, and the displacement here phi n plus 1 is equal to 0. And I have here all the internal nodes, x1, xn, with displacement phi 1 and phi n. And the wave equation has been written that way. Something like this, right? Okay? And so something like this. And then I say that observability in this case, observability means that if phi n is equal to 0, then phi is equal to 0 everywhere. This is the discrete analog of the previous observability inequality, right? In which case I said that phi x at x equal 1 was able to give me an estimate on the full energy. In this case, what is phi x? Well, phi x is simply, as we have said, a multiple of phi n divided by h. But in this case, I am in the finite dimensional context. All norms are equivalent, so proving the observability is just proving this unique continuation property. And this is trivially fulfilled. Why? Right, assume you had already phi n plus 1 equals 0. Assume you have the next node equals 0 as well. Write this discrete wave equation at the node n. And what do you get? You get that phi n is 0. The second time derivative of phi n is 0. Phi n is 0. Phi n plus 1 is 0. What do you gain? You gain that phi n minus 1, the neighboring left, is 0. And once you continue that way, you propagate, and you get 0 every day, everywhere. So you get immediately that you have the observability inequality. So then I can discretize the corresponding functional, minimize, and I have an approximation of the control. What is the paradox if I do it that way? The paradox is that by doing this, I never see the need of taking t greater than 2. Right? So this looks like correct, right? So let's repeat again. So what do? I say, okay, I have to deal with the observability, fine, of the wave equation, fine, but eventually I will have to discretize. Let me discretize from the very beginning. Okay? I replace the corresponding observability, inequality, and functional to be minimized by the corresponding numerical analogs. I check observability, everything is true. The finite dimensional problem is controllable, so actually I minimize this and I get a control. And this control VH should be a numerical approximation of the control of the wave equation.
Yeah, but it's finite. It's finite. It just solves the finite problem.
Yeah, but as h goes to 0, there are, n goes to infinity, there are more and more points, so I am approaching better and better the control of the full wave equation. So this is not really the deal. The problem is that when doing this, I never see t less or greater than 2. I never see t less or equal than greater than 2. So where is there is a gap here in the proof. Well, of course, in this proof, I never proved, for instance, that VH was bounded, right? To prove that VH was bounded, I will need to prove that all these quadratic forms are, uniformly coercive. And in fact, I should check that these observability inequalities here are uniform with respect to H. This is something I never did, right? I just did a very quick argument to say, because H is positive, N is finite, I repeat this argument, I have uniqueness, and I claim now that all norms are equivalent. Yes, but as n goes to infinity, maybe the constants in the inequalities are not bounded. So someone could claim, and that will be a smart answer, well, very likely what happens is that this procedure here leads to bounded controls when t is greater than 2. Right? It could well be that this procedure converges or diverges depending on whether t is less or greater than 2. Right? That will be compatible with the fact that for the wave equation, we know a priori that t has to be greater than 2. Right? Okay, let's see what happens. I do numerical simulation. I take this initial datum. Now let me show you the numerical simulation. So this is the wave equation in the interval 0, 1. I take an initial datum like this to be controlled. I control on the extreme x equal 1. I take a time interval 0, 4, right? And this is the pattern of the control I can compute using Fourier series where everything is explicit, or D'Alembert, because 4 is a multiple of 2, which is, the time needed for the periodicity in the interval 0, 1. I see this pattern for the control. Actually, when you look to the initial datum and the control on the boundary, you see that the control on the boundary is just a mirror reflection of the initial datum, right? Except that now, because time is multiplied by 2, yeah, it's not 2, but it's 4, I have 2 copies with half the energy. And I have an positive part and a negative part. What do you think? Why do you think that I don't get here like 4 peaks upwards and I get some up and some others down? Why do you think that's the case?
Reflection.
Reflection. So in the Dirichlet boundary condition for the wave equation, waves are reflected, but actually when they are reflected, they change sign. These are like swimmers, right? So when they get to the wall, they come back by changing sign. Okay? Good. So the optimal control for the wave equation is this. Well, this is of course in agreement with the fact that the wave equation is controllable in time 2 or more. I have taken time 4, is controllable, and in this particular case the control is particularly simple because according to these symmetry considerations, this is the pattern of the control for this initial datum. Good. So now I do the numerics. Okay, I minimize the corresponding functionals, right? And this is what I get. So with say 20 nodes, I get a quite decent approximation of the control. You see that this piecewise constant function hidden there behind is the actual true control. And with 20 nodes, which is not a very fine approximation, I get this oscillatory approximation to the, piecewise constant function. I increase the number of nodes and I get something similar. I continue increasing the number of nodes, hoping that the simulation will converge. And what happens actually is that it's getting worse and worse and worse. And once I get to 100, 200, I simply get wide oscillations, so meaningless. I get nothing. It's full of noise. And this is not in agreement with our previous conjecture, because our previous conjecture was that something like this could happen maybe when t will be less than 2, but we expected the algorithm will be okay for t greater than 2. 4 is greater than 2, it didn't work. Something else is going on. Okay? Let's check. Okay, so then you say, let me do, well, this is all explained in this paper I wrote back in 2005 in Science Review, where you have a very, elementary presentation of, numerics, wave propagation from a numerical perspective, and what is the impact in terms of control of wave-like equations. So, sorry, I'm going back. I should go farther. Okay. So if you want to understand what's going on, we say, let me do the Fourier representation of the solution of the finite difference wave equation. In other words, because I am dealing with this finite difference scheme, I can simply compute, this is a 3-diagonal matrix, right? This is a 3-diagonal matrix. I can compute the eigenvalues, the eigenvectors, and I can decompose the solution of this, say, second order in time ODE system using the eigenvectors and eigenvalues of the corresponding generator. And this is what I see. What I actually get here is something very close to the corresponding Fourier representation of the wave equation. This is the pure wave equation, right? This is the one we have used before. While for the finite difference discretization, of course, because you have dimension n, you only get n terms. But this is not bad, because when n goes to infinity, of course, these n terms will approximate an infinite series. You get the corresponding eigenvectors, and you get the corresponding square roots of the eigenvalues of the 3-diagonal matrix. Right? It turns out that the eigenvectors actually are the evaluation of the corresponding sinusoidal functions here over the grid points. The grid points being those points in which, the segment is being divided by finite differences. So it could not be better, right? In this, move from the perfect, exact, infinite Fourier series to the finite difference approximation, in this move, the eigenvectors here are exactly the same as the eigenfunctions here, right? So this is really a miracle, because everything is very uniform, and this is the very nice 3D numerical scheme for the constant coefficient Laplacian and so on. So the only really relevant change from here to here is that the time frequencies are not k pi anymore, but are given by these square roots of lambda. The matrices under consideration being tuplage, 3 diagonal with constants on the diagonal, you can compute the eigenvalues explicitly, and you get these formulas. And you see actually that the spectra converge, right? For instance, fix some k, say, let's look to the 13th eigenvalue. Fix k equal 13. The corresponding eigenvalue of the wave equation is 13 squared pi squared. And the corresponding eigenvalue for the finite difference scheme is this. When h goes to 0, this converges to k squared pi squared with k equal 13. So everything is perfect. I see at the level of the finite difference, at the level of the Fourier representation, I see the convergence of the finite difference solution to the PDE solution. It has to be that way, right? But in this case, I see it very clearly. I said, n goes to infinity, eigenvectors coincide, and eigenvalues converge. It could not be better. Okay, what is wrong then? What is wrong? I draw, right, the square root of the eigenvalues, and for the continuous wave equation, the eigenvalues are k squared pi squared, so the square roots are k pi, as in here. So they are aligned in this blue horizontal, blue diagonal line, k pi, right? The gap between one and the other is always pi, 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 right? Because this is k pi. On the other hand, I take these, say, eigenvalues of the finite difference discretization of the wave equation, and when I take the square root, I say this sinusoidal function, and then I see this, this sinusoidal red line, right? I see here a very nice tangency. And this is because the finite difference is a second order approximation of the wave equation. So everything is very nice. So I don't see any complaint about, that, numerical approximation of the spectrum, or if you wish, this numerical approximation of the Fourier series by the finite dimensional Fourier series expansion of the semi-discrete wave equation to justify these monsters.
Maybe you need a stronger conversion of the eigenvalues. Maybe you need that they converge uniformly.
Yeah, but they never converge uniformly, right? So eigenvalues, you can increase the order.
In L2, in little L2.
You can increase the order of the numerical scheme, then you will improve this tangency, but eventually, there will be always some divergence here at the level of the high frequencies, right?
Yeah, maybe that's the problem.
That's the problem, definitely. Actually, if you think in those terms, you say, well, what is actually the main difference from the blue line to the red line? Is not only that this blue line and this red line are getting far apart, but actually the last eigenvalue, the drawing here is not done well. The last eigenvalue here is sitting on the maximum of the sinusoidal function. So this means that while here the slope of the blue line is constant, here the slope of the red curve is slowing down. And what is a slope? A slope is gap, right? The slope is what is the distance between one eigenvalue and the next. So you see here is pi, 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 pi constant, while here is going to be pi essentially in the beginning, slightly less, 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 and when you get here, the gap is that little, is of the order of little h. So the issue is the gap. You remember in Ingham said, don't worry whether this is pure, say, trigonometric polynomial or not. He said, my inequality applies always. The only thing you need is to check the gap, right? And whenever you have a gap, you have the inequality on a given time. But you have to know the gap. Now, I have a wave equation with a gap pi. And accordingly, I have a observability inequality in time too. Now I replace this wave equation by this semi-discrete approximation. And it turns out that for this semi-discrete approximation, the gap is little h. So if I want to establish an Ingham inequality, what is the time I need? It's 2 pi over h. It goes to infinity. Nothing is uniform because the gap is going down to 0. Okay? So if you see explicit observability inequalities for this problem in which you follow the dependency on the dimension n or the mesh size parameter little h, what you observe is that the inequality you get diverges completely. In particular, this is telling you that, this red curve, you need more time to control than for the wave equation. And you say, this is like hard to understand, right? Finite dimensional systems can be controlled in any time. Yes. But if you want the constant in the observability inequality to be uniform, you have to take time greater and greater and greater and greater. Why is this? So this is the monsters. So, okay, this is a monster, right? How you say monster in Chinese? How you say monster?
怪兽.
¿Cómo?
怪兽.
怪兽. Okay. So it's a 怪兽, right? A 怪兽. So this is what? This is, I'm taking simply, just to, do you get an intuition of what's going on? I take for n equals 60, so moderate, not too small, not too large. I take this solution of the semi-discrete wave equation in which I am involving the last Fourier components. This one and that one, which are very close, right? Okay. One with Fourier coefficient 1, and the other one with Fourier coefficient -1. So I am building what is called a wave packet, right? A packet of 2, right? Take 2 waves and put them together in a packet. And then I draw this solution. This is a drawing. There is no numerical approximation. I simply draw this solution in MATLAB. And this is the kind of sinusoidal shape I see, right? Going up and down, going up and down. And you say, oh, this looks like a wave equation. This is time, this is a space. This is a nice wave equation. Yes, but what you see the time periodicity here. The time periodicity here is totally wrong. For the wave equation, the time periodicity of solutions is 2. And here, it's taking like a time of the order of 50 or 60 of the order of the number of nodes in order for the wave to self-reproduce. Why is that? Well, this is the principle of resonances, right? Of wave packets. You see? You say, you have a wave, a signal, size 1. Then you drop another one with a frequency that is very close, mu plus epsilon. So here epsilon is h, is the gap, right? Which is very small. I call it here epsilon because this is a general computation you can do coming from other sources. So now you say this is a common factor of this. Okay? So how much energy there is in this system? There is one here, and there is another one here. So the total energy of these waves, wave packets, is 2, because there are 2 waves, and I get epsilon t plus blah, blah, blah. So what do I see? What I see is that because nearly the periodicity on one signal and the other are nearly the same, what I see is a wave and then an anti-wave an anti-wave that is slightly shifted in time. But when I do the superposition of both of them, what I see is something that is 0, right? How long time I will need by observing this kind of phenomena to realize that something of size 2 is in there? Well, I will need a time of the order of 1 over epsilon, right? So the time I need in order to see in the amplitude of this signal, right, the emergence here of something of unit size is of the order of 1 over epsilon. So the closer are the two frequencies, the smaller is the gap, the longer I need to wait, right? In the beginning, I will not even be able. This is like, did you ever go to make your acoustic test on the doctor? No, I never did. You know, you can check your eyes, you can also check, and then they send you a signal, and then after some time you say, oh, I heard something. Yeah, by the time you heard, the signal was coming for depending on how is your, your quality, right, of acoustic audition, then you will get it sooner or later, right? But here is the same. So the wave was there, 1 plus 1. But because you were only seeing this superposition, you were confused, right? You didn't realize that the total energy of this vibration was 2. It took us that long to realize it. And this is what we are seeing here. We are seeing two waves that nearly, cancel each other. So it takes you a long time before you really observe this wave pattern, right? So what is the remedy? The remedy is not taking t long, because Ingham says you need to take t of the order of 2 pi divided by gamma, and gamma is h. And when h goes to 0, you need to take t going to infinity. You will never be able to do it in finite time. You have really to get rid of the, how did you say the name of the phantom, sorry?
What?
Huh? Washoe. We have to get rid of the washoe, of the phantoms. Because the presence of the phantoms, the presence of these Fourier components in which the gap is very little, is the one that is being an impediment for getting anything uniform, right? So then what you do is the following. You say, okay, out of the finite difference approximation of the wave equation, I take the Fourier expansion of the solution, and everything here in this gray square, I kill it. Right? So meaning that I will not, is it written? No, sorry, it's not written. Sorry. Meaning that I will not consider the finite difference approximation up to the index n, but for instance here only up to index n over 2. If I do it up to index n over 2, what happens? It occurs that then, in this spectrum, I am only considering this part. And in this left part, there is a gap. It's not pi. It's less than pi. Meaning the time I need to uniformly control the numerics is slightly greater than 2. But it's going to be better than 4. And accordingly, I expect numerical results to be better. What happens then? Okay, what I need to do this time is to minimize the same functional as before. I minimize this functional, but I don't minimize among all possible solutions. I only minimize it in the space where half of the solutions have been taken into account. Only those involving the low frequencies. I have established a Fourier filter in which all the high frequency components have been removed. And by doing this, I do the numerical simulation, and of course, despite some oscillations due to the discontinuities of the control, this is typical, this is the Gibbs phenomena, I get a good numerical convergence of the numerics. So everything was related to the gap condition, the failure of the gap condition. The failure of the gap condition is related to the travel time of solutions, and to the fact that, in the original inequality, this inequality was not uniformly true, and this inequality is only true with a constant which is uniform, provided the high frequencies are filtered. Okay? Okay. So now I said filtering in Fourier means that in my numerical code, in which, you remember, the numerical code was out of the adjoint wave equation, build the functional J, then discretize JH, and then it was to minimize JH. Filtering means that rather than minimizing this among all possible solutions, I just take, say, half of the low frequency components.
But why half?
Well, you could take different, yeah, you are right.
Yeah, but finally there's no this time too involved.
Yeah, so if you filter more, the more you filter, the better is the gap, the shorter is the time. And the less you filter, the smaller is the gap, the longer is the time, right? So you give me time, say, what is the control time for the wave equation? 2. And then you tell me, compute the control, well, at time t equal 2, I will not be able to do it. You tell me, compute the control for time 2.1. Okay, 2.1, I filter enough to make sure that the gap is close enough to pi, so that 2 pi over gap is 2.1. And then I minimize over this subspace. But you see, when you minimize in spaces that are smaller and smaller and smaller, what happens? You minimize on spaces that are shrinking. Then when you minimize in a space which is shrinking, the number of derivatives you get 0 at the minimizer is decreasing as well, right? Because at the minimizer, we say that the gradient of J is equal to 0. At the minimizer, we say that the gradient of JH is equal to 0. But how many partial derivatives are involved in this gradient? As many as dimensions are in the space in which you are controlling. So this means what? This means that when you restrict or filter the class of solutions of the adjoint system on which you are applying ingam and obtaining observability, what you are doing at the discrete level is to relax the controllability condition that should be something like this into something like this. Pi yht equal pi h y prime t equals 0. Meaning that you are only controlling the low frequency components, right? So what is the message? The message is that you have to be careful. Depending on what you want to do, there are things that you can and some others that you cannot. If the goal was to approximate the control of the wave equation, you can do it. But in order to do that, you have to use filtering and you have to relax the controllability condition. If the question was more complex, was about, can I control these finite dimensional systems fully and pass to the limit as h goes to 0, the answer is no. This will blow up completely. Okay, and these questions are different, and this is a deep issue, and this is why, even though some people claim I don't need to deal with controllability of infinite dimensional systems because I will discretize everything, and in the end I will use the toolbox of MATLAB, you have to be careful, because if there is no dissipativity on the system, because of this kind of resonance phenomena, you can get something totally wrong. Okay? Okay, so I stop here. I let you then ask questions. We have some time for questions now. Plenty of it now.
I have a question. You said at the beginning that afterwards we understand why it's called distributed parameter systems.
Yeah.
I don't know the answer.
Okay, so yeah, distributed parameter system is because the wave equation is a system in which you are modeling the deformation of every point x. So the parameter is x.
Okay.
And the parameter x is distributed in a domain omega.
Okay.
That's it, right? Well, this is the way I understand it. I'm not sure is that, but I mean, this is the way I understood a terminology that I found always quite strange, right?
And in this case, the control of that objective was what? What we would like to, like when we apply the control law that now we obtain, that
Yeah.
is V, what happened to our system?
Okay, this is what I'm saying, right? So you have to be careful. In the end, you don't know what are you doing anymore, right? So what I said is that if you want to make something that you control, I mean, that you understand from an analysis point of view, my recommendation is minimize over the subspace in which this dark part has been removed.
The thing is, okay, for the finite dimensional system, the lesson that we did this morning, we want to drive our system from an initial state to a final state.
Mm-hmm.
Okay, then in the infinite dimensional case, what is our objective? What is our goal? I mean,
yeah, I mean, our goal was the same. So for the PDE, originally the goal was the same. Was stop vibrations and drive the solution to 0.
okay.
Okay? So this was the original goal. Take the wave equation, distributed parameter system, you know, the parameter being x. So I see that as a system where the state is y and x is like a parameter. This is a kind of a strange way of saying, but I mean, if you can, right? If you are really used to finite dimensional system, you could think that these are like finite dimensional systems or linked together through the variable x. Okay. In any case, this is an infinite dimensional dynamical system, and the question is controllability. Drive vibrations to equilibrium. So once the chord gets to that point, you stop controlling, the string doesn't vibrate anymore. This death. Mark?
Yeah, I have a question. If the control law you found with this methodology is the cheapest, how is it that it doesn't decrease while the system is being stabilized? I mean, it's like it doesn't diminish, right?
No, precisely. But this is what you get by this duality theory and Pontryagin, right? So the optimal control, in the sense of the L2 norm. So you remember, I mean, that was general, right? We said this is the same for wave equation or for the finite dimensional version. It doesn't really matter. So we were dealing with controls like this, right? And we said, if you look for the control of minimal norm, we said the control is B star phi. And phi is a solution of the adjoint system. And then if this operator is anti-adjoint, what you get is something periodic. The control doesn't decay. Why? because the instruction you have given to the control is to be optimal, but to be optimal globally. So what you do is you are swimming, right? You tell me, okay, you have 1 hour to swim. Okay, I take a constant velocity and I swim constant velocity, 1 hour. You tell me 2 hours, I will go slower, and then I have to preserve energy for 2 hours, and then a smaller velocity but constant swimming, right? That is the optimal strategy, right? This is like, well, I didn't run marathons, but those that run marathons, I think they try to do similar, right? So they try to reach soon kind of constant velocity and try to keep it, as long as they can, right? Okay, so this was the goal, and then what I said is that when you are approaching this from the finite dimensional perspective, you have to be very careful. Because, in particular, for wave-like phenomena, the gap matters, right, as we have seen, and is nearly impossible, as we said, so the drawing was here. There is no numerical scheme that is able to approximate high frequencies in a uniform manner, right? So in particular, you could say, well, yeah, but this is for a number of n. So divide h by 2. You take h smaller. So n goes to 2n. So here, you will improve the tangency. But when you will go to the high frequencies, you will see the same pattern again and again and again. So the fact that here, at the highest frequency, when k is close to capital N of the order of 1 over h, you are reaching the maximum for the square root of lambda, and therefore the gap is nearly h. This is something that doesn't cure when h goes to 0 or n goes to infinity. So the monsters will still be there. And the only way you can get rid of them is if you really filter the high frequencies.
There are any simulation of the, like maybe discretized wave equation with the founded control input?
Sorry?
Like in the end, we are coming out with a control law that's come from approximation of the infinite dimensional control law that we could have in the perfect case. And like I would like to see the final results that we would have in discretized wave equation. I mean, okay, we find the control law. What happens if we apply it?
Oh, I see. When you apply to the wave equation, but you can guess very. So this is what you see. So in the 1D wave equation, this is telling you what is going on. What you see inside and what you see on the boundary is basically the same. Okay, so the wave equation is simply, in the one-dimensional case, the wave equation is just a mirror, which is distributing in time on the boundary what you have initially on the initial data. Right? So you have initial data here, and what you see here basically is a copy over the boundary of this initial data. Then if you give me very wild things on the boundary, right, you know that these very wild things will be very good to control very wild initial data, but very bad to control the kind of initial data you had. So, in other words, I mean, I didn't do it, but if you take now this kind of very oscillatory signal and you really say, oh, let me use this to control the wave equation with this initial datum and then plug it in the, say, analytic formula or a very fine resolution of the wave equation, what you will see is that you see the true solution like this plus plenty of noise. Oh, we have to take a picture as well. Right?
It's today.
Huh? Well, our group is today, so tomorrow you can take any other one, right? But the group of this class is today, right? Because we are finishing today. So before we leave, so by the way, tomorrow what is there is this Airbus engineering course. Do you know the speakers or?
Yeah, it's written there.
Well, this is not the answer. My question was, do you know them? I know the names, right? But so that's anyone in the network did have a contact with them previously because you were no? Okay. So you will know them tomorrow.
Actually, still I don't quite understand why do we need this continuous analysis. I mean, it's not enough to use just the discrete one.
Right.
Yeah, because actually the initial condition we can also impose as a discrete one. So everything is discrete, and we use the discrete version of wave equation.
Well, this is a test, right? So of course, yeah, numerical analysis is always done.
Yeah.
On test examples where you can actually check the accuracy of the result achieved. So, but now, precisely, assume we say, okay, you lecture 15 hours, very complicated. I finally take the wave equation, I discretize, and I use the toolbox of MATLAB. So then what you get is this.
But this, I think, can also just be explained by discretization of this numerical scheme. For example, like the high frequency cannot captured by default because you have just a discrete version of everything,
right,
including the initial.
Right. So then you have to filter, right?
Yeah, the filter process is also quite reasonable.
Right.
Because
right. This is what I'm saying. I mean, nothing here is very complicated. The point is that if you want to make it correct, then you see that you can discretize. Of course, you can still continue discretizing the wave equation according to the classical recipes, finite differences, but you have to filter. I'm telling you a little bit more. I'm telling you that filtering affects how long you need to wait on the control process.
Yeah.
So it's quite subtle, right? You say, how much I filter? Half, 1/3, 7/8. Where do I put the filtering parameter? And does it matter how do you place the filtering parameter? It does matter. And actually, to understand this well, the best is to go through Ingham inequality and the gap condition.
But the price of is all the time control. That's also the price to pay.
Yeah, basically here, yes. Basically here is the once you realize that, then everything is fine.
But even though you intuitively, if you take off half of the set and you minimize just half of it, it seems like a high price to pay. But still, you just get like more time. That's the only thing. Like when you minimize on a subset, you are taking off a lot of chances to actually get the real minimum.
Well,
and you just take like.
I mean, you are right. So actually,
To me, that it's like it's not a high price to pay, but I don't know what is the relation between like increasing the set, increasing the time of control.
so you have also to take into account that in the end, numerical algorithms are always a compromise between accuracy and computing time. I mean, computing time matters as well. So in particular, if you have to do a lot of filtering, you are adding plenty of time to your algorithm. So you have to really try to figure out how this filtering is going to be done and how much it's costing you. Okay, so in the end it's not that expensive because you can use Fourier, fast Fourier transform and things like this, so this will not be much expensive. But this is something you have always to do, right? So, and more nowadays where, all numerical schemes are available, all computers are available, all software are available, you can implement the method you like. So it's not only a matter of what is the error, but rather how long it takes you computing. And maybe this is what they will tell you tomorrow. I mean, this is the challenge, in companies. I remember the last time I heard a lecture by someone in Airbus. He was saying that, okay, so we have methods, they are good and fine, and we can do it a steady state, Navier-Stokes. We do one simulation. The problem is it takes 4 hours. One. It's too expensive. So you have really to reduce, right? And then all methods are needed in order to become more efficient at that level. But indeed, from an analysis level, assuming that the cost of solving numerically things is not taken into account, that this is done by the computer for free, right? Then, indeed, we could say that the only price to pay and the only thing in which there is some degree of choice or arbitrariness on what I explained is that the time of control depends on the filtering parameter. So actually what happens is that if D'Alembert says you introduce some initial perturbation, this produces a front propagating with velocity 1 and the other one with velocity -1. If you simulate that numerically, you see plenty of shadow. You will see a signal with velocity 1, a signal with velocity -1, but many other weaker signals. Here. Plenty of numerical, say, noise here inside. Do you know why this kind of array arises for the finite difference discretization of the wave equation, while the true wave equation is only producing these extremal waves with velocity 1 and -1? Yeah, these numerical errors, this is the numerical dispersion.
Otherwise, this should eliminate completely each other.
Actually, this is what we see here. This is what we see. So you see, gap is related to the velocity of propagation. So actually, when doing the finite difference discretization of the wave equation in this red diagram, we are producing waves with velocity of propagation 1, but also wave with velocity of propagation 1/2, waves with velocity of propagation 1/4 up to h. And this is what you see here. This is wave with velocity of propagation 1/2, 1/4, and so on. So actually, and this is something to be understood and is often confused, the numerical analysis theory says that a numerical scheme is convergent provided the numerical scheme is able to reproduce the physical solutions. But nobody says that the numerical scheme will not produce phantoms. Okay? So the classical convergence analysis of numerical schemes for PDEs is not sufficient when you ask more to the numerical scheme. Here we are not asking the numerical scheme only to converge in the classical sense of numerical analysis. We are asking much more. We are asking to be able to reproduce in an accurate manner something that is quite fine and is related to the very precise way waves are propagating on the wave equation with velocity 1 and bouncing back and forth on the boundary. And this is what gives you the time of control equal to. This is not easy to see. And this is a very important warning for the numerical approximation of control problems. Control properties of distributed parameter systems or infinite dimensional dynamical systems can be very hard to be seen numerically. So for instance, let me give you an example. You will understand this better. This is a very simple example. This is related to damping stabilization. So take the wave equation. I mean, this is an exercise you can do. How many exercises do you have? How many there were?
40,
Huh?
like that.
34.
Okay, so last one. So the damped wave equation, compute in Fourier series the damped wave equation and check what is the decay rate. So you take the wave equation in the interval 0, 1. Right? So this is a damping term. This is the same as for the harmonic oscillator. You remember I was putting this minus k x prime term. Damping is the same. So here, if I write the energy, 1/2 integral of yt squared plus yx squared dx from 0 to 1, the time derivative of the energy is minus k integral from 0 to yt. Yes. Minus k. Now I know from my experience with the harmonic oscillator that very likely the decay rate is not monotonic on k, right? You remember there was some kind of saturation threshold. You remember the decay rate was, k damping and then decay rate, and then I had something like this, right? There was this overdamping phenomena. Okay. Okay, let me now do the drawing of how the spectrum looks. So we are on the complex plane. When k is equal to 0, this is a conservative wave equation. We have, the spectrum is on the imaginary axis. Of course, I have infinitely many eigenvalues, right? Ik are here. Here and here. Okay? Now I put some damping k. And then the spectrum moves to the left. I put some damping, and then the spectrum moves to the left. Right? But as it happened in the harmonic oscillator, they are losing also height. When I hit the first, say, critical value, this one, they collapse here, the others are still here, but all the eigenvalues are still on the vertical line. After I go beyond this critical value, one moves to the left, the other one to the right. And when k is large enough, I will have, a number of real eigenvalues here, and the other ones over there. Okay? So this is the behavior of the spectral behavior of the continuous wave equation with damping, right? You do boundary damping and you will get more or less the same. You get exponential decay. Now, what is the amount of exponential decay you get is delicate, right? Because, on one hand, I wanted to put a lot of k to push, the decay to be very fast. And this is what this is telling me, this kind of vertical line. For the high frequencies, the decay is very fast. Yes, but for the low frequencies, I'm paying here very low decay because of this overdamping phenomena, right? So there is always a compromise. And it's hard to push all the spectrum uniformly, right? So this is the fact that, you know, the spectra, these are non-self-adjoint operators because this is a damping on a conservative system. So these spectra are not self-adjoint, so they are on the complex plane. And there is no way of pushing a complex spectrum in a uniform manner. You know, you push here and then the others are moving in the opposite direction. So you have to be very careful. So the design of dampers is delicate. This is what this is telling me. It's very delicate to design dampers, because the damper that might increase decay on a number of Fourier frequencies may be deteriorating the decay in others. So making a uniform compromise all along the spectrum is a delicate thing. Okay? Good. Now you do typically numerical approximations of these spectra. So you discretize this by little h, so you get finite dimensional components n. So what is what you expect? I mean, ideally you will say, oh, then it's very simple, you will get the first n. Well, it's not true. So typically what you get when you are doing numerics, because of the same reason as in here, is that you will get that, you know, the first few eigenvalues are quite well approximated, but after a while the others will get quite far. So in particular, it's very hard to compare what is the relation between the decay rate of the continuous waves and the discrete waves. Right? So then, if you give me waves in this three-dimensional cavity, and you put here a damper, some kind of, acoustic baffle, absorbing waves, in order to damp, waves, and you ask me what is the decay rate, this is not going to be an easy matter. In 1D, I can do explicit computation. In multi-D, nobody knows. And this is actually related to the geometry of the billiard. It's very complicated. So then you say, okay, no problem, I will do it in the computer. Yes, but the computer will never tell you what is the decay rate, because the computer is able to give you a good approximation of the low frequencies, but for the high frequencies you will miss it completely. So numerically, for say distributed parameter systems or for infinite dimensional dynamical systems, it's very hard to do the fine numerical approximation and the determination of the qualitative properties of those systems, because the difficulty of really getting into the high frequency components. So here I have done the wave equation in 1D with boundary control, which is kind of baby model for this, but you could ask many questions related to the to the long time behavior for nonlinear waves right? Or Schrodinger equations, or water waves, and it's very hard to deduce from pure numerical observations what's going on. So numerically, it's very hard to say whether something is correct or wrong. So I show you this numerical phantom. I'm sure you will be happy if I don't tell you that this is wrong. I tell you, well, I have done this numerical approximation in finite differences with the wave equation, and I see these vibrations going up and down. And you will say, oh, MATLAB is so great, right? You get such a beautiful, colorful numerical representation of the vibrations of the chord of the guitar. Yes, except for the fact that this is totally wrong. According to this, the periodicity of the wave equation is 50, while it's 2. But how can you see that numerically? I mean, the computer is only giving you this kind of drawings. Of course, people that are good in numerics, they will tell you, they will do things like Richardson extrapolation, right? They do a simulation, they never rely on one simulation, they divide the step by 2, then they compare, and then immediately they see whether there is something wrong or not, right? Because if I do this simulation with n equals 60 and I see this, then I do, okay, let me divide h by 2. So I do this simulation with 120, and then I see that the periodicity has doubled, I say, oh, something is wrong there, right? You agree? But then you have to have this numerical intelligence, computational intelligence, to be able to say, determine whether something you are seeing is a numerical artifact or something true. So this is actually what happened to Lorentz, right? When he did this numerics of this three-dimensional, say, nonlinear dynamical system, he got a trajectory and then another one, and then he said, well, there is something wrong here. No, there was not something wrong. I mean, he was doing the numerics right. What happens is that there is such a big sensitivity on the solutions, is that when you change a little bit the parameters, the trajectories are totally different. This is chaos. Right? So in his case, the fact that he was getting strange things on the numerics were not related to the numerical default. It was due to the actual dynamics. But again, you need analytical understanding to be able to say whether these apparent numerical pathologies are real or pure numerical phantoms. So these are, say, high frequency, these are called high frequency spurious numerical solutions. So these are residues that are unwanted. But the price to pay for getting the core of your wave equations is that you pay these high frequency, say, noisy components as well. So we take a photo? Good. So anyhow, tomorrow I will be here for this, to make sure that everything works well, and also, of course, because of my interest.